Okay, Mr. Westwater here, and I'm about to go through the ladders question from M2 June 2015, question 4. So we've got a ladder, AB, so I'm going to start with my diagram. Okay, so I've got my ladder, AB of weight W and length 2L has one end A resting on rough horizontal ground, so that means A's on the floor. There we go. So let's label this A, and the other end B rests against a rough vertical wall. So there we go. They're both rough, so we know we've got friction going on in both cases. Okay. The coefficient of friction between the ladder and the wall is a third. So mu equals a third up here. Let's call it mu W, and then this can be mu G. The coefficient of friction between the ladder and the ground is just mu. Friction is limiting in both A and B, so it's going to take its max value, and friction is, where are we? The ladder is at an angle theta to the ground, where tan theta is 5/3. Let's work out the other values of this straight away. So tan theta equals 5/3, therefore sine theta is going to equal 5 squared 25, add 3 squared is going to be 34, so over root 34, and cos theta will be 3 over root 34. Okay, the ladder is modelled as a uniform rod. Okay, so that means we've got a distance of L, and then this weight W is going to be coming down, which lies in the vertical plane perpendicular to the wall. Find the exact value of mu. So before we get going, there's a couple of other forces I should probably label. We've got a reaction force at the wall perpendicular to the wall, so let's call this RW. We've got a reaction force at the ground called RG. The ladder is going to want to slide down, so we've got a friction acting up, and that's going to be a third times RW because it's mu R. And the ladder is going to want to slide out, so again we've got RG times mu G going there. Okay, we've got some other forces going on, so I'm going to start going for some different colours now. Let's break this down. This is going to be W times, in fact I might go for a slightly darker green. This is going to be W, and theta will also be here, so W cos theta, so W times 3 over root 34. And I'm going to go blue. W times 5 over root 34. And up at the wall, we're going to have, well, this angle will be theta, and therefore this angle will be theta. And so we have our perpendicular force, which I was doing in green, wasn't I? It's going to be RW times sine theta, so that's times 5 over root 34. Okay, and I'm just going to remodel this slightly because we've got this other force going on up here as well. So if I break this force down, okay, it's going to have a, again, perpendicular and parallel to the ladder force. Now we have, let's see, I think we're going to have another theta here, because this angle and this angle will add to 90, and these two will add to 90, so this angle here must equal this angle here. Okay, so this other force is going to be a third RW times cos theta, so times 3 over root 34. I don't actually need the parallel forces, so I'm just going to leave them for now. Okay, I think that's just about everything I need. So let's get going. Let's start with moments. So let's take moments around A, leaves us with L times W times 3 over root 34 is going to equal, because both of these forces are going anti-clockwise up at B, I forgot to label this B, so that's going to equal 2L times RW times 5 over root 34, add 2L times a third RW times 3 over root 34. Okay, so if I simplify this all together, we've got, and actually I could multiply everything through by root 34 as well, so we've just got LW, so 3LW equals 2LRW times 5, so actually let's make that 10LRW plus 2, in fact we've got a third times 3 here, so this is just going to be 2LRW. Okay, and actually L's in everything here as well, so we've got 3W equals 10RW plus 2RW, so 12RW equals 3W, oh sorry, W, so the reaction at the wall, if we divide both sides by 12, it's going to be a quarter W. Okay, and carrying on from here, we could resolve perpendicularly. So let's see what goes up and what goes down. We've got RG going up. We've got a third RW going up, and the only thing going down, I believe, is W, the weight. So RG we don't know, but RW we do. It's a third now times a quarter RW. Oh sorry, not RW, just W, isn't it? Okay, W, which is a 12th W. So the reaction at the ground is going to be 1W minus a 12th W, which is 11/12 W. Okay, and so finally, resolving horizontally, I know that RW equals RG times mu at G. So altogether, RW we have is a quarter W minus, oh sorry, no, and then is going to equal 11/12 W times mu at the ground. The W's cancel, so we end up with a quarter times 12/11 equals mu at the ground, and therefore mu at the ground is going to equal 3 over 11. Okay. Does it need it to any greater degree of accuracy? No, it doesn't. Here we go. 3/11.